Hi everyone, my name is Stein. I'm the founder of Adept Materials. In this talk, I want to introduce you to a technology called multifunctional materials for managing moisture and heat in buildings. Buildings account for nearly 40% of our primary energy use, so we all want our buildings to be energy efficient. But we also want our buildings to be comfortable, durable, and affordable. This is asking a lot of building materials, because these demands are typically in tension with one another. To illustrate the challenge, let's look at this residential wall assembly. We can increase the energy efficiency by adding lots of insulation and by tightly installing panels to stop drafts. So these material layers will trap heat, but they also trap moisture, and that makes the wall less durable and the building less comfortable over time. We fix those problems by adding more layers, weather barriers, vapor barriers, to control moisture. But the complexity of the wall is increasing, and that significantly raises costs. Is there any way to avoid these trade-offs between efficiency, durability, comfort, and cost? Nature is a place we can look for inspiration. I'm always amazed by the way plants adapt to their changing weather and even changing seasons. Their magic comes from the transpiration process, where the plant redistributes moisture within its body and releases water vapor from tiny pores in its leaves. I think a next generation of construction materials could mimic that behavior to improve buildings without the usual trade-offs. I'm going to describe a two-layer material, illustrated here, that we call the multifunctional material. It provides directional control over water vapor, it regulates humidity, and it regulates temperature. The physics behind this is moisture redistributing and exchange of water vapor with the environment. It's kind of like a rudimentary leaf. Directional vapor control means that the material allows water vapor to pass through in one direction, let's call it forward, at a much higher rate than in reverse. This is important because if water finds its way inside a wall cavity, we want it to be able to escape so mold or other moisture problems don't take hold. But when the weather conditions change and water vapor is being driven into the wall from outside, we want our control layer to remain shut and protect the inside of the wall. The directional material actually creates a pumping effect too that removes moisture from the wall cavity. It collects water vapor from both sides when the humidity is high, but when the humidity falls, water evaporates from the material in a directional way. More comes out in the forward direction. This two-step pumping cycle happens every 24 hours. So at night, our material collects water vapor from inside and out, and in the day, the sun comes up and drives the moisture to the outside. These properties provide real protection against moisture damage. Blueberries are about the most mold-susceptible things on Earth. The ones on the left are protected by our directional material, which allows the blueberry's own moisture to escape out the top, while preventing water vapor from entering from below, where we put some standing water just to give it a challenge. The blueberries to the right aren't protected by a directional material. Instead, it's a conventional smart vapor retarder. The directional films have a big impact. The hygrometer on the inside of the container on the left only reads 80% relative humidity, and 5 months later, we see no sign of mold growth. The container with the smart vapor retarders, on the other hand, shows a humidity above 90%, and over 5 months, the container of blueberries has turned into a container of mold. The material has two additional benefits. The first is humidity control. If the humidity starts rising inside the building, the material will absorb the excess vapor and sequester it away. And if things start to get very dry, the material releases water vapor and restores the previous balance. The second benefit is latent heat storage. When the sun comes out and makes water evaporate from the material, there's a strong cooling effect, absorbing heat. And the effect goes into reverse when the temperature falls, water vapor condenses in the material, and heat's released. With this final slide, I'll illustrate how a multifunctional paint can do much more than just decorate. We applied 2 patches of paint to a substrate. The one on the left has our multifunctional material, and the one on the right is a conventional latex acrylic. An IR camera shows that the multifunctional paint cools by more than 2 degrees when the material is moved into a relatively dry and warm environment. In conclusion, we're learning from nature to create responsive, multifunctional materials in order to improve building envelopes. Thanks.